Hi, it's me. I'm making this for physics. Hold up, the camera is kind of dirty. I should have checked that first. Sorry. Oh, you missed it. You know, that was an ice cream truck right now. I was passing. I should have got some ice cream. No, because then you would have started judging me about how it falls on my hand. But I hate it. Oh, look, it's the numbers. It's way better than fish. Anyway, so we're gonna do the. I'm gonna try to do the practice test. I haven't done it, but I mean, I'll give it a shot, I guess. So let's see. Oh, I sent myself it. Since I can't like log into Schoology from here, I have to send it to myself through email. Look, can you see my cursor? It's like it turns to different things. Like it's like a little finger, then it's the person highlighting, then it's a little like fairy thing moving the mouse. See the wee, and then it turns to the little finger. Boop 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 boop. Anyway, that's not. Wow, already a minute in. This is gonna be a long video, by the way. I'm not gonna separate this into chunks because this is more like this isn't really me trying to tell you how to do it because all you need is the equations, which I do have right here. So basically, look, it's a Disney castle. I bought that at Disneyland. It's a castle. It's a 3D puzzle though. It took me forever to put that together. Anyway, so here, look, I wrote all the equations down. So this is what you want to do. You want to memorize all of these. I know, right? A lot. But as soon as you go in to take your test, write them all. That's what I did. I wrote them all down on a paper. Just take one green sheet and write all your equations down on that green sheet. So just remember, like, cram these into your head. Just be like this, all of these, all of these. Now that I see it, it looks like a lot. But when I was studying it, wasn't that many, to be honest. So you take these and you cram them into your little head. I mean your big head. Oh wait, which one's better? I guess they're both kind of bad, huh? Never mind. Okay. Already off to a great start, aren't we? So I need help. So you write them all down and then okay, so what I'm going to be telling you basically in this video is because you said you don't know when to use them, so this is my shot at trying to explain when to use them. Okay, I hope you can learn something from this, and keep it lively so you don't fall asleep while you listen to this if you watch it at all. All right, so let's get started with number 1. So it says, how much mass should be attached to a vertical ideal spring having a spring constant, force constant, so K, variable K, of 39.5 newtons per meter so that it will oscillate at 1 hertz. Alright? So let's write that down. So it's going to be... Oh, it feels weird. I haven't done this in a while. Okay? So it's going to be K equals 39.5. That's a 9, by the way, not a 4. There you go. And frequency equals 1. So this, a hertz is the frequency. Frequency is hertz, which means cycles per second, I think. Yeah, I don't know, don't quote me on that. So you have K and you have F, and it's asking you what should your mass be. Now we take a look at our good old trusty equation sheet here, and we'll try to find the one that we need. So this tells us this is K here, but we don't have acceleration or anything like that, so that's not going to be that helpful. This one could be used here because, see, we're going to have it. Frequency is equal to 1 over t, right? So, like, for most of these equations, you're not going to get it, like, I mean, for some of them, you're going to get it, like, right off the buck. Like, I mean, right, like, just from the get-go, your equation is going to tell you everything. But for some of them, you're going to have to, like, piece together like three different equations to get your answer. But that's what's so useful about writing them all down is because look, so first we need to have to find this one, right? So we have m. Well, we want to find m, but we have k, but we don't have t. So like, okay, so how do I find t? That's why you look around and you want f. So you're gonna in order to complete this equation, you're gonna wanna, I mean, you have f. So in order to complete this equation, you're gonna need to get an equation that like has both t and f in it in order to complete your pair, your group. So you look around, right, and then you find here's a f. That's different. Never mind. Let's go back to that one later. So there's, and it's little f. Like fancy F is for frequency, big F is for force, and little t is for time, and big T is for period. Okay. So we only have like one really f. Oh, we have f, and then we have this f, but this f gives us velocity and length, but we don't. So we don't have any of that. So let's not worry about that. So it's this one. So you can write those down if you want over here too. It's just gonna be f equals 1 over t. And don't worry if this feels like it takes a long time, because you have a lot, like, it's honestly very short. The test, it's like not that long, especially for like having a long period and after school. Like I was able to do it all in like after school only because like, yeah, I did not know anything and I had to study like at 2 o'clock and then come back to take it. So yeah. So anyway, and then we have t equals to 2 pi square root of, what is it? M over k. So now you need to, so you have f. So we can do this right away instead of trying to substitute everything. So 1 equals 1, 1 over, 1 equals 1 over t. So then t equals 1. Okay, so you go boop, back over here. 1 equals 2 pi square root of mk. Oh, and the way I memorized this one was, I was like, is it k over m or m over k? And then I looked at it, I was like, mk, because it's like mk, right? Mk. So mk. So what is m over k? So, what am I doing? What am I doing? See, I space out sometimes. I have no idea. We'll get there. We'll get there. Okay, so it's m over k equals to 1 over 2 pi. Now we get the square root out of here. M over k equals square root, or just 1 over root 2 pi. And then k, you can flip it all over, so it's k over m equals root 2 pi. So then k is equal to, oh wait, we need to find m. Oops, I shouldn't have done that. I forget. So it's going to be m, come over here, m equals to k over 2 pi. Okay. Okay. So now we have k is 39.5. I didn't burp, I hiccup. So 39.5 over square root of 22 2 pi. Can't talk apparently. So m equals to, a good thing I really like about physics, I guess, that's the fact that we get to use a calculator. Oops, like that's me trying to do all the calc tests because they're annoying. So many y. Okay, so 39.5 divided by root 2 pi. 15.76. Kilograms? Yeah, kilograms. Okay. So which answer is that? Oh. Oh, mixed mass will be attached to a vertical. Okay, never mind. Oops. See, reading the question helps a lot. So I got a really wrong answer, and I guess it's because it says vertical, So that means gravity is involved. So that means we should have picked the. We could have used this one. Actually, no, we couldn't have because we don't have x. Mm. Let's see. This one? No. Okay. But anyway, you get the idea. This one wasn't on the test, so you shouldn't worry about that. Yeah, there's no vertical springs in the test, so it's okay. Man, I really should have practiced beforehand. Oh well. You're like probably thinking it's like right excited, but nope. Okay, so next one. A package is oscillating on a spring scale with a period of 4.6 seconds. Time t equals 0. The package has 0 speed and is at x. Okay. What time after t equals 0 will the package first be at x equals 4.15? There wasn't one like this either, so I don't even know if I should try to do it. Because I'm pretty sure for this one, it's giving you x's and it's giving you period and time. So you can look at here. I think it's gonna be this one. Oh wait, amplitude. See the problem? So I never really had equations for amplitude. I mean, like, it's coming up with the amplitude is hard because there's no like kind of straight up way of getting amplitude. Yeah, but anyway, you won't. That's not on the test, so don't worry about it. We're skipping number 2. I'm sorry, I just have no idea how to do this. Can you tell I'm underprepared? Yeah. Oh, this is wavelength, but obviously we don't have to do that. Never mind. Next one. Okay, I'm gonna skip these. These are hard, but they're not on the test, so don't worry about it. Okay, don't worry about it. This one. So I'm gonna skip. I'm gonna only do ones that were like actually on the test because, well, I mean, there's no point of you killing yourself over doing these. Like, oh my god, I don't know how to do them. Well, me neither, but they're not on the test, so hey, it's okay. Nobody cares. All right. I'm not gonna waste your time. I know you're a busy girl. You need a grill. Like, boop, boop, boop. You know, sometimes I just stare at it. I'm just like so distracted. I'm like so bored. I'm just like, ooh, look at me. I'm just like, boop, 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 boop. I hypnotize. Okay, I'll stop. Okay, so a guitar string is set into vibration with a frequency of 512 hertz. How many oscillations does it undergo? So it's basically how many cycles does it undergo each minute. Now remember, frequency is cycles per second. So what you want to do with this is going to be, so it's going to be 512 cycles per 1 second, and it's asking you how many cycles in each minute. So you just simple good old conversion factor, which is going to be 60 seconds in 1 minute. So all you do is multiply them, and then you get, so it's 5. Oops, it's off. Oops, I can't type. Times 60. That's 3072. That one. So, I mean, there's only 3 significant figures. That's why they took away the 2 from here, but that's okay. Hey, good job. Next one. See, like the ones that are on, he was super nice on this test. Like, they were all really easy. My arm is hurting. In simple harmonic motion, when is the speed the greatest? Simple harmonic motion. Okay, so just when is the speed the greatest? This is one of the clicker questions, I think. So this one, no work. It's just conceptual. There was only like two, I think, that were conceptual on the actual test. So I wouldn't worry too much if you don't get it. But anyway, so the speed is the greatest when like, okay, so let's, I don't have any kind of spring here, but so basically in simple harmonic motion, right, something goes like this. It goes like shoo, 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 right, like this. So the speed is gonna be least at the edges where, because it goes from here and then oops, stops, comes back, right? Stops, come back, stops, come back, stops, come back. So the speed is gonna be least there, we know for sure. And since it's accelerating here, so it's gonna be, so it's gonna like, so stops, accelerates, accelerates. Once it gets to the middle, it's gonna stop accelerating and start decelerating. So it's gonna be like this, so like really slow motion is gonna be like this. So it starts here, right? So it's gonna be like doot doot doot, and then wait, like doot like that. I mean, I couldn't really tell anything, but basically, like, so let's say these are your endpoints, right? So this is gonna this particle, so it's gonna go. Let's say it starts over here, so it's gonna go like, it's gonna start. It's go slow, 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 fast, 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 faster, faster. But then it has to get fast and then slow. And I have to come back, right? Shoot. Starts accelerating fast, 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 slow. Comes back. Fast, slow. Slow. Like that, see? So the speed is going to be greatest in the middle because that's when it stops accelerating and starts decelerating. So okay, so let's look at these answers. This makes no sense. Actually, never mind. Yes, it does. So your displacement is your distance from the thing. So when potential energy is 0, that means that, so the potential energy is greatest when it's here because it stops moving, right? Because it has to turn around. So that right at these points, potential energy is maximum. So that means here in the middle, potential energy is 0. So that's the right answer. And then when the acceleration is a minimum, actually, yeah, it's a minimum because it stops accelerating. Or does it? No, yeah, it does. It stops here because like this is what happens to the acceleration in numerical terms, I guess. So it gets positive, 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 positive. Once it hits the middle, it becomes negative, right? And then, but since it has momentum, it's gonna keep going. Just the negative part is gonna start slowing it down. So it's gonna be negative, 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 positive, 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 negative, negative, like that. Okay. So when the acceleration is a minimum, that's also true, I think. When displacement is a maximum, no, displacement is 0 at the middle because that's where it starts. So no. When potential energy is a maximum, those are the endpoints, so no. When acceleration is maximum, no. Because that's the endpoints also. So what we learned today is that it's going to be A and B. So we're going to write that down. I hope that's right. Let's see. Are we right? Moment of truth. 4, 5. Hey, we got it. Good job. Boop. Oh, if we got 4 right too. Yay. And 3? Oh, we didn't do those. Oopsie. Oh my god, it's so long. There's 40. What? 50 questions? Are you kidding me? Wow. We better be skipping most of this. because this is gonna be a long video. Oh my God, 50 questions. Are you ready, Carol? Hope you found a good place to sit. Hope you got comfortable. It's gonna take a while. We've only done like 2, and it's already 20 minutes long. So it's gonna be a long day. It's gonna take forever to upload too. Anyways, 6. An object attached to an ideal spring executes simple harmonic motions. If you want to double its total energy, you could. Okay, so look at your trusty equations. There's ones for energy, which are this one. Your total energy equals to 1/2 Ka squared all the time. It never changes. It's always down. So what you want to do to double its total energy, which is E, you want to double K or root 2A, because that will give you double. Okay, but I'm pretty sure root 2A is not going to be a choice. But anyway, so double the mass. No, your energy has nothing to do with your math. Double both the mass. Why can't I say it? Mass. Double both the mass. I keep wanting to say math. Oops. Oh, what? Low battery. Excuse me. Hold up. Let me charge this before it dies, because we're gonna be here a while. Oops. I charged. Struggles. Okay. So you want to double force constant K. Good job. That's right. Double both the amplitude and force constant. No, because I will give you. So it's going to be 2 squared 4 times 2, 8. It's going to 8 times your energy, which is not what you want. If you double the amplitude, it's going to increase it by 4 times, not twice. So it's only going to be C. Yeah. Let's write that, okay? What is it? So this is 5. 6 is going to be C. 7. An object attached to an ideal spring oscillates with an angular Skipping that one. That one's not on the test. There's nothing angular on the test, okay? So don't worry, you're pretty little ahead about it. An object is undergoing simple harmonic motions, amplitude, okay. Velocity, this one we can do. Oh no. There's no angular ones, but this one is easy. Because, is it easy though? You know what? We're running out. This is a long test. Let's not do it. Okay, let's see it. A 3.42 kilogram stone hanging vertically from an ideal spring on the earth undergoes simple harmonic motion. Vertical springs, nope. The length of a simple pendulum with this one's good. Okay, so this is a pendulum problem, so we'll do that one, okay? But it's really easy, okay? So all I give you is period. So big T equals 2 seconds. Okay. Now you look at the trusty equations now. Now there's 2 period equations, okay? 2 period equations. This one is for springs, strings, everything else, waves, whatever. This one, pendulum. This one is for a pendulum. L over G is for pendulums. So you want to write your equation down. So then T is equal to 2 pi root L G. Now you want to find L. So all you do is, so it'll be 4 pi, right? Because 2, you move the 2 pi. Oh, you divide, never mind. So it's going to be 2 over 2 pi, so it's 1 over pi equals root LG. Like the brand. Woo! So it's going to be 1 over pi squared equals to LG. So then L is equal to G over pi squared. So then L is equal to 9.81 divided by second pi squared. Oh my god, I almost put clear instead of enter. Oopsie. 0.99, so it's going to be 0.99 equals 1 meter. Okay? Which is, which one? 7. Hello? Or was it 7? Oh no, it wasn't 7, it was 10. Wow. Wow. Oh wait, I mean, this one, basically, okay? That's what we got. I thought I was going to round it, but apparently not. So it's B, okay? BB. BB8. Next one. Bungee jumper jumps off, undergoes, okay. Period, okay. Oh, mass. This one should be easy. Okay, so a 51.8 kilogram bungee jumper jumps off a bridge and undergoes simple harmonic motion. If the period of the oscillation, so big T equals 11.2, what is K, spring constant, of the bungee cord, and mass? So they give you mass, they give you T, big T, and you want K. So now, this one is easy because you just need the you look at your little equation sheet, right? So here's the equation for T, right? They give you T, they give you mass, and you want K. So you just need one equation for this one. So it's pretty Gucci, pretty bougie, pretty good. Okay. So you just move stuff over. Old switcheroo. So T squared over 4 pi squared equals M over K. Flip stuff over. So it's going to be 4 pi squared over T squared equals to K over M. And then 4 pi squared M over T squared equals K. So K equals mass, what's the mass? 51.8. You can't see. There you go, better. But now I can't see. What was I doing? Anyway. Oh, okay, 11.2 squared equals 16.3 newtons per meter, which is number B. Dun-dun. Yay! See, so they're pretty straightforward. Carol, just write all your equations down here. Have that sheet next to you when you take the test. I mean, obviously, you're gonna have to memorize them for like a minute, I guess, or like 10 minutes, depending on, just go in the room, just like stare at all the equations, recite each one of them, then go take your test on your phone quickly, write them all down, and then you'll have this. It's like cheat sheet. It's like, remember the flashcards for last year, yeah, how everyone passed because of those. Just make your own flashcard, but like right then and there, and then you'll be good. Honestly, I should have done this for like all the other tests, but whatever. Okay, so now on to the next one. Next to the on one. There you go. An object is attached to just whenever you see the word vertical, just give up. Air track cart is attached to an ideal spring force. What? Air track cart? I mean, I think it's just mass. Yeah, this air track cart part, just ignore it. Well, we'll see. If we get it wrong, then I guess it matters. But if we get it right, then it doesn't matter. Doesn't matter. There's not one like this on the test anyway. Just doing this so you can get an idea of what you're supposed to do. And T-way. So K equals to K is equal to EVIN or AROL 3.58, and that's one mass equals 0.15. Okay, now what's the period of oscillation? So just same thing again, remember. So this one's way easier because you don't even have to move anything around. You just get K. So it's 2 pi square root of 0.15 over 3.58. So all you do is plug it into your calculator and you're good to go. Let's do that. How about that? How about them apples? I had an apple today and it was disappointing. I wanted it to be like cold and like hard, but it was kind of like like half mushy, and I don't like that. I want my apples to be like, I like them to be hard, and like juicy, not like soft and like soggy. Like, what is that? That's not an apple. That's a fail apple. Those apples don't deserve to exist. Point what? 0.15. K 3.58. 1.28. So 1.29. 1.29 hertz or seconds, I guess. Yeah, seconds, because T is seconds. Is that there? Yeah, right there. Yay! B. Boop, boop, boop. Next one. 14. Oh, more air track cards. Yeah. Next. See you later. Identical balls oscillate with the sorry. With this the same period T on Earth. Ball A is attached to an identical spring. I don't know why, but I just imagine like Perla's face like balls. I love balls. Ooh, look, shells. Identical spring and simple pendulum. Oh, okay, this is just a what do I call it? Conceptual problem. Okay, so there's a problem on the test that says an astronaut, whatever, has a pendulum that has like a period of this on Earth, like a period of, let's say, 2 hertz on the Earth, and he takes it to the moon or to an asteroid, and it has a period of 11 hertz or something like that. So then the question is, what's the force of gravity on the asteroid? So in order to do that, you just use your T equals 2 pi square root of L over G, and you just solve for G, and that's pretty easy. So this is like that, but it's no numbers. It's just, there's G equals that. So see, this one's different because it says ball A is attached to a spring and ball B is on a pendulum. So the spring shouldn't change. Oh, actually, yeah, it should. No, because the spring shouldn't change, but the pendulum should. Because a spring, remember, the spring depends on mass and K. Actually, the spring should change too, because mass is going to be different because it's different gravity. No, mass doesn't. I'm so dumb. Mass doesn't change. I thought, wait, no. So the spring does not depend on gravity. It just depends on mass, which stays the same. But the pendulum depends on gravity, so that's going to change. So on the moon, oh, wait, what? Okay, so they both have the same period to start with. So when you have less gravity, the period increases. So when you so ball B will take less. Yeah, so ball B will execute more vibrations each minute than ball A. Wait, that one's true. That's not true. That's true. B and D are true so far. So it's B and D. Okay. Yay! Could you even see? Hold on. Let me. So it's B. Ball B will execute more vibrations, and D, ball A will take longer because pendulums. So ball A won't change at all. Oops. What is? Oh, you just. Hey, my hand. Hello. So pendulums change with gravity. Springs don't. So ball A will stay the same, while ball B will get faster. So yeah. There you go. Next one. Oops, we just did 15. I really need to renumber these. You know, I shouldn't even number them before I get to them because I end up skipping like most of them. Horizontal friction friction. Yeah, nope, skipping that one. Acceleration, velocity, no thank you. Yeah, nope, skipping that one too. Okay, this one's not that bad. So it says 18. There's not one like this on the test, I don't think. But it says 0.25 kilogram harmonic oscillator. Or you can just imagine like a mass on a spring. It's like the same thing. Has a total mechanical energy of 4.1 joules. If the oscillation amplitude is 20 centimeters, what is oscillation frequency? Now this one you're going to need two different equations. So let's look at our trusty equation sheet. So we want frequency, okay? So the only equation for frequency we have is 1 over t, or you could use this one. Velocity over tau. So, do we have velocity? No. So we're going to need to use 1 over t. Yeah, we're going to use 1 over t. So let's write that one down. And, okay, so now we have t. So what do we need? We have energy. Oh, okay. So we're going to have to use this one because it gives us energy and amplitude. So, and then we need to find k using that. And k will help us because we need also to for this equation over here for t. So we need t equals 2 pi mk and e equals 1/2 ka squared. So now first we need to find k, and then when we find k we need to find t, and to find t we need to find f. Okay? Or we could just try doing this. No. Let's just work on it one by one. It's easier. Instead of trying to combine all of them, we can just do them one by one. Get the same thing anyway. So, first we're going to solve for k. So we divide by a squared and multiply by 2. So it's going to be 2e over a squared equals k. So then k, its total energy says it's 4.1 joule. So 4.1. I'm going to rewrite centimeters into meters. So it's going to be 0.2. Yeah, so it's going to be 2 times and then 0.2 squared. So k is equal to 2 times 4.1 divided by 0.2 squared. Right? Yep. 205. Wow. Okay, and then when we found k, we have to go back over here. So t equals to 2 pi square root of m over k. M is 0.25, and then k is 205. So t is equal to 2 second pi times root 0.25 divided by 205 is equal to 0.219. Now f is equal to 1 over 0.219. So then f is equal to 4.56 hertz, which is 4.6 hertz. Yay! If I'm going too fast, sorry. I guess. I don't know. There's no way for me to really tell, I guess. I don't know. Next one. See who's on me more now, huh? Get on my level. Number 19, maybe? Complete one oscillation with simple harmonic. Nope. No position ones. There's no position ones, okay? So don't worry about that. Simple harmonic maximum displacement. Nope. No angular whatever's. Ooh, a supermarket. Okay. Oh wait, but there's gravity, I guess. Yeah. No. No thanks. Yeah. No. An astronaut has landed on an Oh, this one. This is the one. Oh, it's exact. This exact one is on there. I didn't even notice. I didn't even do this practice test, but anyway. Okay, so the pendulum has a period. Which one is this one? 22. So it has a period of 2 seconds on Earth, and then the period increases to 11.3 on an asteroid. So period. So but T Earth is equal to 2 seconds, and T A asteroid is equal to 11.3. Now, so T is equal to, for a pendulum, it's a pendulum, remember? So it's 2 pi L G. Life's good. Not really. So it's going to be, so then what we want to find is we need the length, because we don't know L and we don't know G. Well, we know G for Earth, but we don't know G for this one, for the asteroid. So we need to find L first, because we have T. So then you just remove stuff, so you divide, so it's T over 2 pi equals square root of L over G. So then T squared over 4 pi squared equals to L over G. So then L is equal to G T squared over 4 pi squared. So L is so T is 2, so it's 4. 4's cancel. It's going to be G over pi squared equals to 9.81 divided by pi squared to 0.99. So length is equal to 1 meter. Okay, so now we just use this for this one. So we make a TA equals to 2 pi root of L over GA. So that equals to 2. Okay, so now we can just reuse this. We can work from here. Instead of solving for L, we just go for G. So then we go G over L equals to 4 pi squared over T squared. So then G equals to 4 pi squared L over T squared. So then G equals to 4 pi squared. So that's L is 1, so it's 4 pi squared over, and then T squared is 11.3 squared. So we just do our little thingy. Boop, 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 boop. Let me check how much battery this has in case it's okay. It's charging. So it's gonna be 4 pi squared over 11.3 squared equals 0.31 meters per second squared. Now let me make sure this is correct. Which one is this one? 22. Oh wait. Which is, yes, it's here, I guess. Yeah, 0.307, which is A. Let's check it. Check. 22. A. Yay. Oh look, we're 22. Oh, almost halfway done. Yeah. Good job. A ball is attached to an ideal spring and oscillates period of T. If the mass is doubled. Okay, this one's good. This one's like, you just look at your formula, right? T equals 2 pi M over K. So if the mass is doubled, then what happens to the period? For these, it's like calculations, but not really. So you just write down your, which one is 23? It's going to be T equals to 2 pi K. So then your mass, so that's your T1. So then T2 is going to equal to, and then M2 is equal to 2m1. So then it's equals to 2 pi square root of, so m1 here, so then 2m1 over k. So now you can move stuff around, so it's t2 over 2 pi equals, oh wait, never mind, I don't know what I'm doing. So I mean, you oh, okay, so what you do now is so I thought I knew how to do this, but apparently not. So you want to find out what T2 is in terms of T1. So oh, okay, so what you could do, I guess, so this whole thing equals to T1, right? So what you can do is you can somehow try to get rid of this, like pull that out, which would be root 2. You can just pull out a square root of 2, because square root of 2 times square root of m1 is going to be square root of 2 times m1. So you can just pull out the root 2, so it'll be T1 is equal to root 2 times 2 pi root m1 over k. So then so ignore that. So then T2, remember this is this, so T2 is equal to the square root of 2 T1, which is E. Yay! Next one, 24. Oh wait, actually it's not numbered. We don't know. Papers everywhere. Yeah, nope. Let me see. There we go. Simple harmonic point is the magnitude of instantaneous acceleration, the greatest. A and D. Just cause. Remember, acceleration is the greatest instant. Oh wait. Velocity would be 0 here. Acceleration is the least here because this is when it changes accelerations. But it should be A and D because, well, it's gravity, so gravity, like the or is it C? I think it's, no, it's C. No, I mean, it's always the same, isn't it? Acceleration, because, but I guess you also get an acceleration to the left and to the right. Yeah, I'm not sure. I'll guess A and D. Let's see, that's right. It's E. Oh, which number is that? 24. 24E, 24E. Yeah, okay, I was right. So yeah, because it's the pivot points is where acceleration is the greatest. 24E. Okay, let's just write the big old E here. E for easy, am I right? Kidding, I'm kidding. Christmas time is here. A Christmas ornament made from thin hollow glass sphere hangs from. That's dangerous. I mean, oh, never mind. They're all all the old ones used to be glass. Okay, G. So this is. Oh, I get it. This is a pendulum problem, but it's like the pendulum where like the fat pendulums, like the pendulum where the mass isn't on the, or is it? Oh, small hook, I guess. I don't know, but it's too much. There's nothing like this on the test, so let's not deal with that. Christmas, it's not Christmas right now. Nobody's problem. Phase, okay. Well, finally we get on to chapter 14, which is sounds and stuff. So now it says 2 in-phase loudspeakers are some distance apart. They emit a sound of frequency 536 Hertz. A microphone is moved between the speakers along with a line joining the two speakers with a constant speed of 1.6 meters. What beat frequency is observed? There was no beat problems at all on the test, like at all. And I was kind of disappointed because that's like the one thing I knew in the beginning was how to do beats. You know, the beat drop. It's real. So yeah, I was like, wow, there wasn't a single one. I was like, wow, okay, whatever. So let's see. Huh. But this microphone is moving? Well, I mean, there's no beats problem, so we can skip that, right? Yeah, yeah. Good. A tsunami. And tsunami. An ocean wave generated by. Okay, we know that. Okay, propagate. What's its frequency? Yay. Okay, so. Now these. It says. It is. So it's the speed of the wave is 700 kilometers per hour. So we can write that. Kilometers per and then wavelength, which is tau, is 750. So then what's the frequency? Now this brings us to our other half of equations, which is all for chapter 14, which is sounds and waves, sound waves and stuff, or just waves in general, I guess. So this equation, velocity equals tau frequency. So velocity equals tau frequency, because we have tau, we have velocity. So when you want to know what equation to use, you look at your variable. So I guess I'll start doing this from now on. Is you write down what you have, and you write down what you want, and you look for equations that use equations that have all three of them, and then that way you can move stuff around to get what you want from what you have, you know? You get what I'm saying? So now we have velocity, we have tau, wavelength, and we want f. But it's set up so we find velocity. So all we have to do is move it around, which you know how to do because you're smart. And it's that. Bam. So now all we do is 700 over 750 equals 0.933, and there you go, 0.93 hertz. Yay, which is D. Okay, you got it. Feel free to take a break, pause the video, and I'll be all done. I'm kidding. There's still like half the test to go, and it's already been like an hour. Oh my god. Damn, this is long, bro. What? I'm so tired. I don't want to do this anymore. Let's keep going. We're halfway done. Wow. Jesus Christ. Okay. An hour with Carol. Oh my god. How beautiful. How amazing. Oh my god. You are driving along a highway. Ooh. Got to take the high road always. You are driving along a highway at 25 meters per second when you hear the siren of an emergency vehicle. Okay. Traveling at a constant speed in the opposite direction on the other side of the highway. When the vehicle is approaching, you hear a siren as 238 hertz. But when it is past you, the frequency becomes 1680 hertz. What is the frequency of the siren? So okay, so for this one, okay, so there was this one, I think, exactly on the test, but this was the last one, and I kind of ran out of time because he was rushing us, so I didn't get to do this one. But I'll try it now, I guess. So this one is when the sound source is moving, or you're moving, and there's an equation for that, which is the one I told you I was going to get back to, is f prime. This one, ba-bam. So the top part is for when you are moving, and the bottom part is for when the source is moving. When the listener is moving, and when the source is moving. But when they're both moving, use this whole thing, and the F's cancel. I think, yeah, they should. Okay, so I don't know. I don't know. So you're gonna 20 what? 29. So it's gonna be, so your velocity, u observer equals to 25.0 meters per second. Now it says traveling at a constant speed in the opposite direction. So I'm gonna go on a whim and say that it's traveling at the exact same speed as me, but the opposite direction. So velocity of the source is equal to negative 25.0 meters per second. So it's coming toward me. Okay, so the first frequency right here is equal to 2380 hertz. And the second one I hear is 1680 hertz. And the speed of sound is 343, so this velocity of the wavelength is this good sound. Now, these equations, let me write them down. F prime equals 1 plus or minus u observer over velocity times F over 1 minus plus u source over v times F. Now, so these plus or minuses is because you have to pick one depending on what's happening. So the first one of both of them is when it's getting closer. So when the observer is getting closer to the sound, it's 1 plus observer whatever F. When the observer is getting further away from the sound, it's 1 minus. Now when the source is getting closer to you, it's 1 minus that, 1 minus the speed of the source over the velocity of the wave, which is the speed of sound, which is 343. And when it's getting far away, when it's leaving you behind, then it's 1 plus. So in this case, the observer is getting closer to the sound, and the sound is coming closer at the same time, which is for the first part. So this first frequency is a result of you getting closer, the observer close, and the source close, right? So they're meeting like this, so boop, and then boop. Now this second one is due to you getting far, so the observer this way, and then the source is now this way, and now you're getting farther apart. So that means the source is going farther apart, and the observer is going farther apart. The observer, so it's going to be 1. So for the first part, so F prime, so it's 2380. This is going to be a long problem, by the way. So it's going to be 1. So you're getting closer. You're getting closer to the source. So it's going to be 1 plus the speed of the observer, which is 25 meters per second. Should I have a negative or I guess let's figure that out, huh? I'm not sure. This will teach us whether or not. So it's gonna be that, which is 343, by the way, over 1 minus. Let's just keep it the same for now and see if we get the right answer. Okay, so it's gonna be that. So now we have. So we want to what are we trying to find exactly? Oh, the base frequency. Okay. Huh. Are these equations written correctly? They might not be, for all I know. Oh, I guess you can develop a Like, okay, so I think this one's tricky in the part where in the sense that you have to remember last year, I think, or was it this year, like honors physics, or was it AP physics, where we had to do like reference points. So let's say like I was traveling at like 5 miles per hour on the train, right? The train was traveling 5 miles per hour, and there's a person like standing there, and then so the person standing there sees the train as like coming toward them at 5 miles per hour, but the person on the train sees the person coming at them at 5 miles per hour. So if the car is going, so I guess you double the speed then, because if you're approaching at 25 miles an hour and they're coming at 25 miles an hour, then you double it, because it's you're getting closer at the rate of 25 miles per hour and they're coming closer at the rate of 25 miles per hour. So if you were to think of it as you standing still, you would see the car coming at you at 50 miles per hour. So that's what we're going to do. So scratch that, because we need to find F, but this does not give you F. So so what you do is going to be only use one of them. So, and let's pretend that I'm standing still, so the source is coming toward me. Okay? So it's going to be, yeah, because it says the observer hears the frequency of the siren, so it's better if we do that. So it's going to be 1 over, so it's coming closer at me at a speed of 50 miles per hour. Meters per second, I mean, whatever. 50 miles is going to run me over. So it's going to be 50 over 343 times F. Now we want to find F, right? So it's going to be, do a simple switcheroo, or just multiply by F. No, yeah, so we switch them around. So F is equal to 1 over, yeah, right, so you multiply by F and you divide by F prime. So it'd be 1 minus 50 over 343 times F prime. So it's going to be, so that's going to be 1 over, hold on, we can't even see that. 1 minus 50 over 343. You know, if you can also just like play these in double speed, I guess. That way it takes less time. You know, you get to sleep earlier. And 380. Okay. So the frequency is 4.9 times 10 to the negative 4 hertz. Okay, yeah, you know what? I'll just admit I'm lost. I don't know how to do this one. Next one. That one's hard. Okay. Same thing. It's the same exact thing as the police siren. We're not doing that one. No beat frequency. Okay, I think this one was on the test too. Oops, why am I holding it vertically? So it says a distance 15 meters from a sound source, the intensity level is 60 decibels. What is the intensity level at the point 2 meters from the source? Okay. So for this one, we look at your trusty equation. Okay, so let me write stuff down like I said I would, like 3 questions ago. So R equals 15 meters. Burger King equals 60, and so then R2 is equal to 2 meters. Okay, so we have R and we have the B, fancy B. So now, and we need, hold up, and we need intensity level, which is B also. So we need B, question mark. Okay, so let's look at our equations. So 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 we can use this one because this tells us R, but we need to find the beat here. I'm trying to find if there's any other equation we could use, but I don't think so. I think we're stuck with this. But it doesn't give us power or I. It just tells us B. Oh wait, we can find I. Never mind. Okay, so we need to write down this first. So B is equal to 10 dB times log of I over I naught. Right? Probably gonna do this wrong, but intensity level is decibels. Yeah. Okay. Okay, so it tells us that. Okay, so now we need to find what I is in order to use the other equation. So we divide B by 10, and then so equals log I over I naught. And then I think it's, how do we pop this out? We do, it's e to the B over 10 equals log, no more log, I over I naught, right? So then I is equal to I naught e to the B over 10. So I is equal to, and then I naught is one that is a thing that they give you. Let me try to find it. Threshold of human hearing. I think it's 10 to the negative 12. Let's see. Hopefully it's here somewhere. And it's not. Well then. He gives it to you on the test though, so you don't have to memorize this. Like on the test it tells you what I naught is. You can't see anything, sorry. But I can't even type because my keyboard's like hidden under all these papers. Why? So it's hold up. Let's see. Threshold of human hearing. There you go. Stop it with your zero. I need to know what the I intensity is. Why? Hopefully, when you go to images, it's usually better. Please, 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 please. How could this happen to me? Oh wait, I don't know why I'm. Oh, duh, it's I naught, bro. I'm trying to figure out what that is. I don't know. Actually, I forgot that it's here on this thing. So let's see. Let us see. No summary. Superposition. Blah blah blah. I need to know. No Dopplers. Stop it. Oh. So yeah, I wrote that equation wrong really bad. So you have to put the F there on the outside anyway. Okay. My bad. I thought that they canceled out, but they don't. So it's that. So write that equation down. Okay? Properly. Okay, here it is. Yeah, 10 to the negative 12. I knew it. Such a pain. So it's 10 to the negative 12 times E, and then your bells were 60 bells? What? Was it? Where am I? Question 30? No, I don't. Not 30. It's 32. 60, yeah, 60 decibels. 60. So it's, hello, can you focus, please? Thank you. So 60 over 10. So I equals 10 to the negative 12 time, no, not there, times e to the 6 equals 4.03 times 10 to the negative 10. So now we can use that. We can we need to use this to find out, using our other equation of I equals p over 4 pi r squared. So now our r was 15 meters. So we need to find p. So p is equal to I 4 pi r squared. So it's equal to that times 4 second pi times r squared, which is 15 squared, which is 1.1406. So we use that. We use this over here, and to use our new radius, so it's going to be I equals p over 4 pi r squared, so it's equal to 1.1406 over 4 pi times 2 squared, which is equal to so it's equal to 2.269 times 10 to the negative 8. And now we plug this I into, well, you can see this I into this equation to get our decibels. Ugh. So it's your bells equals 10 times log of 2.269 times 10 to the negative 8 over 10 to the negative 12. So it's equal to 10 log alpha, whatever, this divided by 10 to the negative 12, which is 43.56 decibels. That was annoying, and it's not even an answer choice. Well, hell then. Let's see which is closest to it. Let's just pick B, whatever. There wasn't one like that though, not really. Next one, lowest tone to resonate in a pipe L that is open at both ends is 20 hertz. Okay, so it's telling us that, so this is one about 33, this is one about harmonic intervals. So it's going to be F1, your lowest harmonic is going to be this, and it's open on both ends, so it's this one. So it's F1 equals V over 2L. So it's telling us the lowest pipe, it's going to be 200. The fundamental frequency is that. So our velocity is equal to 200, and the length is, it doesn't tell us. And so what? Oh, and the velocity is 343 because it's the speed of sound. So then L is equal to 400, and then 343 over. So L is equal to 0.8575. That's our length there. So it's telling them which of the following frequencies will not resonate in the same pipe. So it's telling us, well, I mean, B is obviously wrong because that's the one they gave us right now. So we need to find out the second harmonic, which you just take this one and you multiply it by 2. So that'll be 4. So that one exists. 3 exists. they all exist except for E, because that's not a, because once you start going up from here, this is your fundamental harmonic, then you just multiply by you multiply numbers, and since this is 2, every multiple is going to be a multiple of 2, because it's going to be 200 times 1, 200 times 2, times 3, times 4, times 5. So times 2, times 1, times 2, times 3, times 4, that's not times 5. 200 times 5 is 1,000, not 900. So this one's wrong, so it's E. Okay, am I speaking too fast? I want my throat's getting dry. Turning factory whistle. I can't whistle still. Can be heard up to a distance of 2.5 kilometers, assuming that the autistic oh my god acoustic output of the whistle is uniform in all directions. How much acoustic power is emitted by the whistle? Why can't I speak? The threshold. Oh wow, it was there the whole time. I was looking for it too. Why didn't I find it? Whatever. Okay. So it's giving us R again. And we want power this time. I don't know why it's giving us I naught. I don't think we need it. And it's asking us for power, yeah. So we just need I. Oh, okay, so it's going to tell us. So what this is basically telling you is that at 2.5 kilometers, the sound frequency, like the power becomes this. Okay, so let's write that down. So power equals 10 to the negative 12 at radius 2.5 kilometers, right? So now, and it's asking us for power 2 at radius 2 . Oh no, it's just telling us that. So it's asking us for no, okay, so I'm dumb. So I is equal to that at this radius. So it's asking us for power. There you go. So the threshold of human hearing. So so sorry if I'm just ending up confusing you. So intensity. So this is your intensity at this radius. So intensity equals P over 4 pi r squared. So P is equal to intensity times 4 pi r squared. So it's equal to 10 to the negative 12 times 4. Should I use? Okay. So it's going to be 4 pi times what? Times 2.5. I'm going to put that into meters because I guess it's better that way. So 2.5 kilometers, so you just put 2.5 and you multiply it by 1,000 to get it into meters. 2,500 squared. So it's going to be 10 to the negative 12 times 4 pi times 2500 squared equals 7.85 times 10 to the negative 5. So this is only one with a 7 in it, so it's that one. It's E, okay? Yay. Oof. If a wave has a speed of 362 meters per second and a period of 4.17 milliseconds, what is the wavelength? Okay, this one's easy because it's just so you look at your good old, okay, so never mind. Promises aren't being kept, right? So velocity equals 362 2 period t equals 4.17 milliseconds. Okay, so we have v, we have t, and we want tau. Now we're gonna look at our trusty equation sheet, and let's look. So let's see, boop, 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 boop. You know, I'll let you figure out which equation we use. Okay. Boop, 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 boop. It's like a metal tape. It's like beep 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 That was a bad idea. Now my throat hurts. Damn it. Anyway, in case you didn't figure it out yet, it's this one. It's like Dora. Can you click on the right equation? That's the one. Can you tell how crazy I'm becoming? I mean, I'm always like this, but you know what I mean. Oh, what? I'm so lost. Okay, so velocity equals tau frequency. Oh, okay, so then frequency, remember, equals 1 over period. So we substitute that, so velocity equals that over time, period. So we need that, so we just velocity times period. So it's 362. And now we want to change milliseconds into seconds, so it's just multiply by 1,000. 4.17 times 1,000. Oops. No, it's divided by 1,000 because they're milliseconds. You're turning a smaller number into something bigger, so it's 0.00417 seconds. So it's 362 times point. Oh, I'll just use this answer. 1.509 meters. What are we doing? Oh, this one. Yay, 1.51 meters. There you go. It's a 36th. If a wave has a speed of 362 meters per second and a period of 4.17 milliseconds. We just did that one. A music tuner uses 554 hertz C-sharp tuning fork to tune the frequency of a musical instrument. If the tuner hears a beat frequency, there's no beats, sorry. A pipe of L, length L, is open at both ends and resonating at its fundamental frequency means F1, okay? Which statement about the sound is correct? Okay, this is just a conceptual one, so we can chill with this one. The wavelength is 2L and there is a displacement node at the pipe's midpoint. Oh, you have to read the chapter to understand this one. We're okay. There's nothing like this, okay? Don't worry about it. There's nothing really conceptual on this test. It's just equations and knowing when to use them, which I'm trying really hard to tell you, but I'm failing really hard too. Sorry. Crests of an ocean wave pass a pier every 10 seconds. If the waves are moving at 5.6 millimeters per second, what is the wavelength of the ocean waves? Okay. Crests of an ocean wave pass pier every 10 seconds. So it's giving you velocity and it's giving you period, which is 10 seconds. So it's giving you period, it's giving you velocity. So, let's write that down. Kevin, how about that? So it's period equals 10, velocity equals 5.6, and tau equals question mark. So remember, we want to use our equation. Tau f, and then f is equal to 1 over t, so velocity equals tau over period. So then tau equals velocity times time period. So tau equals 2, 5.6 times 10, which equals to 56 meters. Wow, which is B. Yay! Next one. In a resonating pop. I can't. What? Are you telling me I skipped 38? I went read 39? Or is it the same one twice? Oh, there is this. It is the same one twice, kind of. Antinodes and more antinodes, whatever. Tripping. In many cartoon shows, wow, a character runs off a cliff, like Bugs Bunny, and then their head stays there. Fan, why you do this to me now? Yeah, it says a character runs off a cliff, realizes his predicament, and lets out a scream. He continues to scream as he falls. If the physical situation is portrayed correctly, from the vantage point of an observer at the top of the cliff, leaning over the edge, the pitch of the scream as he falls should be. The pitch should stay the same. Well, actually, no. Okay, so we can look at the glug glug glug. You make it sound like I'm drinking something when you say glug glug. Okay, I'm not drinking anything, so stop. Okay, so we can look at an equation to see what changes. So a pitch basically means frequency. Okay? So we can look at our frequency equation and see what affects it. So frequency is affected by tau, wavelength, and velocity. So since they're accelerating, their velocity is getting bigger and bigger, so that means the pitch should increase. So it should be increasing as he falls. Yeah, it should be increasing as he falls, okay? Do you understand? Ooh, like Goofy when he falls. I can't really do it because my throat is like really dry. No, it's like I can't remember. I'm sorry. Don't make fun of me, okay? Stop. Wow, I did. I wrote this on my equation sheet instead of actually. Wow. Okay. It's A. That was 40. Oh, my phone unplugged. Gotta put that back. Okay, next one. A crane lifts a 400 kilogram beam at a steady rate of 15 centimeters per second. Needs a steel cable. Let's not do that one. There's nothing like that. You are driving along a. It's the same one. I swear. Look, 42 highway police. You are relieved. He's in pursuit of a different driver. Let's look. 29. Oh, it's 35 instead of 25. It's the same problem. Wow. Well, it doesn't matter. We're not doing it. Can you hear him upset? You are moving very quickly toward a speaker emitting a pure tone. Which characteristics of the sound get larger? So you're moving towards something. Remember our equation for moving towards something? Right here, the top one. Yay. Focus, please. Okay. So as you're getting closer, your frequency increases. That's it. Really. That's... Oh, and your sound intensity increases because yeah, because your R is getting smaller, so your intensity increases and your decibel. So loudness, which is intensity D, and frequency C, get louder. The wavelength, the period, all stays the same. Okay, yeah, it does. Right. Yeah, so intensity gets louder and your frequency gets loud. Okay, so frequency and loudness. So it's C and D. 43 is C and D. 44. Two steel wires are stretched with the same tension. The first wire has a diameter of diameter. No. Why? There's nothing like that. A 2.31 kilogram rope is stretched between supports that are 10.4 meters apart. It has a tension in it of 49.2 newtons. If one end of the rope is slightly tweaked, how long will it take for the resulting disturbance to reach the other end? So it's asking for period, and we have mass and tension and length. Okay, so let's write all that stuff down. So it's mass equals 2.31. Bum 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 bum. Length is equal to 10.4. Tension, which is, we can write that as force because tension is force. 49.2. Okay, and it's asking us for T. Now we look at our equations, and okay, so we find T. Now T is equal to 2 pi square root of m over k. But we don't have k. So we could try to, so, and then also T is equal to 1 over f. And then f is equal to velocity over wavelength. So we have m, we have L, and we have force. We don't have wavelength. We don't have wavelength though. Oh wait, no, we don't. Wait, what? M over k. We don't have k though. We're not gonna get k at all because that's not possible, bruh. Okay, this one's challenging. So like I think we could. So this one is good because this one is for tension in a rope. It gives us force here, and then this mu is equal to m over L. So that means velocity equals to square root of f over m over L. And then when you can use this velocity equation here, but then we don't know what this is. We don't know what tau is. So we can try to find an equation for tau. But I mean, chances of that, I mean, it can't be harmonic because it's not a string, it's a rope. I guess we could just give it a shot and go for 2L. Yeah? Should we do that? Okay. Let's do that and see where it goes. Wow, an hour and 30 minutes. You've been here a long time. I had no idea it was going to be 50 questions. What? Okay, so which one did we? Okay, so velocity equals the square root of FL over m. Then velocity is equal to tau force. Tau is equal to 2L. And then force is equal to 1 over T. So T is equal to 1 over F. And we need T. So then we can just substitute this in. So 2L over T, well, you can't even see, sorry. 2L over T equals square root of F FML. No, it's FLM, but it is FML right now. FML, you know. So you can't even see. Sorry. We have L. We have M. We have F. So we just need to find T, right? So we can do the good old switcheroo. So it's T over 2L equals to the square root of M over FL. And then we do T equals to the square root of M over FL times 2L. So T is equal to the square root of 2.31 times 49.2 times 10.4 times 2 times 10.4. Let's write that all down on our trusty calculator. Second square root. What? Oh, I put enter by accident. Alpha, whatever. So it's going to be 2.31 divided by 49.2 times 10.4 times 2 times 10.4 equals 1.39 seconds. It's not an answer. Okay, so we can just say the wavelength is equal to L, so instead of a 2, so it's divided by 2, so 0.7 seconds. 69 seconds, which is A. Okay. So like most of the time these, like, you could do it wrong, but then if you can like kind of understand how you got it wrong, like how I just did, is that I mistakenly took tau to be 2L, but it's actually only L. The wavelength is only the like I had thought about it, but I wasn't too sure. So when you're dealing with like ropes and stuff that aren't like sound waves or anything like that, then your wavelength is going to be the length of the wave, which is as far as it can go, which is the length of the rope. Okay, so there you go. So it's going to be 1.39 divided by 2, because the 2 doesn't exist anymore, so it's 0.699, which is A. Oh my god, so long. 46. Which of the following curves shown in the figure best represents the variation of wave speed V as a function of tension for the transverse waves on a stretch string? So we kind of wrote that already. So V as a function for tension. Okay, so it's going to be FLM. And it's a square root function, so it's going to go like this, right? Whoop. Okay, square root. There you go. So it should be B, actually, because it's the only one that looks like a square root. The rest are negative and stuff. So it should be B. Hope you understand. Hope you understand. Okay. Remember, you can ask me questions too. If you don't understand, just be like, hey, what did you mean when you said this? And I'll be like, okay, you know, you could feel free to actually comment something. You know, you're the only one who's there. No one's gonna make fun of you for commenting because no one's gonna see it. Okay, so let's see. Well, first let me see if I'm right. 46B. Bum bum bum! Yay! We got it. You can't see because it's blurry. There we go. Dun dun. Next one. Oh, so close. The string of length L is under tension. The speed V. What will the you can't even see. What will be the speed of a wave in the strength of the length is decreased to 2L, but there is no change in tension. Okay, so we can just look back at this equation, the FML. Where is it? It's up here. So if L is increased to 2, remember we pull out the root 2. So then V is equal to root 2 root FL over M. So V2, then V2 is equal to root 2 V1, right? So it's going to be V root 2 again. So it's C. So we're right with that one. Yeah, we got it. Got him. Two motors in a factory are running at slightly different rates. One runs at RPM, this one runs at 7. Well, you hear the sound intensity increase and decrease to wave interference. How long does it take between successive instances of sound intensity increasing? What? There's nothing like this, so don't worry about it. My excuse to say nothing. The lowest tone to resonate in a pipe L, okay. Oh, okay, this one's different because it says the lowest tone to resonate in a pipe of length L that is closed at one end but open on the other end is 200 hertz. So now, these equations over here, trust the equation sheet. It's here, fundamental frequency, but you see how there's another one? This is for ones that are open at only one end and closed on the other. This is for open at both ends, or a string, and this is for a pipe closed on one end. And then when this is the case, you only get n equals 1, 3, 5, etc. You only get odd numbers. Okay, so we can, so it's going to be 200 hertz, right? So then 49. So it's going to be, so f of 1 equals 200. So then f of 2 is going to equal 4 times. No, it's going to be it's not going to be f of 3. It's going to be f of 3 is going to equal 3 times that. So it's going to be 600. And then f of 5 is going to equal 5 times 200, which is 1000. F of 7 is going to equal 1400. So 600 is there, 1400 is there, 1000 is there, 400 is not there. So it's going to be A. Okay? Got it? Bum, bum. Final stance, final ones. Or the last one, actually, very last one. Come on, Carol, we made it this far. Gotta do this. You're moving at a train towards you are moving at 100 toward a stationary. Okay, this one's easy because it's stationary. Thank you. The train blows it's 4.4 kilohertz whistle. There you go. You heard it? I can hear it. Damn, it must be really loud. The speed of sound is 340. What frequency do you hear? Okay, so this one's easy. I mean, you look at your trusty equation, right? It's gonna be this one, and you are moving toward the thing, so it's gonna be the top one, and the train is stationary. Okay, so it's gonna be f prime equals 1 plus u observer over velocity times f. Now f original is 0.4 kilohertz, but you can just multiply that by 1,000 to get it in hertz, which is 400. So it's going to be 1 plus, and your speed is 120 kilometers per hour, which is, that's really fast. No, actually that's pretty slow. Oh, it's kilometers per hour. I can't really change that. I'll have to change that to meters per second. Yeah, no, I'm gonna have to change it. Okay, so 120 kilometers over 1 hour times 1 hour in 6,000 seconds times, so now we're in seconds and we need meters. 1,000 meters. 1 kilometer in 1,000 meters. So we just multiply. We set up a little thingy, so it's going to be 120 times 1,000 over 360 equals 100 divided by 3, which is 33.3 bar meters per second. Okay, so it'll be 1 plus 33.3 over 340 times your first frequency, which was 400. So it's going to equal, so you just put 1 plus your fraction, 33.3, for good measure, 340 equals, and then you just multiply that by 400. We get 439.2. Yay, 439 hertz. It's D. And with that, we're done. Good job. Thanks for coming to class today. You can go home now. Go cry to your family. I'm kidding. Not really. Anyway, I hope you found this useful. I hope you leave a thumbs up if you liked it. Make sure to comment, like, subscribe. Wow. I don't know. Hope you learned something, I hope you had a good time too. Laughing at me at least, If you weren't laughing with me, at least you were laughing at me. Anyway, goodbye, Carol. Remember, you'll be fine. It's not a bad. Just remember, write down your equations, write down your givens and what you need, and just stare at your equation sheet for like 10 minutes if you have to. It's okay. You have plenty of time. Just do it, okay? They're not hard. You got this. You're smart, okay? You're good. You don't doubt yourself, Carol. You got it. You'll be fine, okay? So, bye-bye. See you next week. I'm kidding. Oh, actually, see you tomorrow, I guess. Anyway, goodbye. Oh, wait, you complete the other half. You know what it is, right? Bye-bye.